Cool. We'll go ahead and we'll get started with our first presentation, PFAS Risks, Status, and Opportunity with Dr. Bruce Rittman from Arizona State University. I'll hand it over to you, Bruce.
Okay, thank you. And let me know when my screen, my slides are showing. Do I need to do something again here? Maybe I do. Okay.
Looks good to me.
Okay, good. Okay, and I even got the laser pointer. Wonderful. Okay, well, thank you for inviting me to talk about PFAS, one of the hottest topics in the environmental business this day, maybe the hottest topic of all. So let's start off by what is PFAS. So the acronym stands for perfluoroalkyl and polyfluoroalkyl substances. These are organic molecules that have a lot of fluorine substituents on them. And if you look at the left-hand side of my slide here, you'll see two of the really prominent ones, PFOA, that's perfluorooctanoic acid, and perfluorooctane sulfonate, PFOS. And first of all, both you see the word octane, so both of them have 8 carbons. And we go look here, 1, 2, 3, 4, 5, 6, 7, 8. Both have 8 carbons. And you can see the molecules are just loaded with fluorines, except for the end here. There's always a functional group. So this is the one PFOA is an example of a carboxylic acid. And of course, this is a sulfonic acid here on the end. But all the carbons in here that could have a fluorine group attached have a fluorine group attached. So for PFOA, you've got 15 fluorines, and for PFOS, you have 17 fluorines, but they both have 8 carbon chains. These have been very heavily used PFAS molecules over the decades. There's also polyfluorinated ones, and one that you'll be familiar with, everyone's familiar with, is polyfluoroalkyl, excuse me, this one here, which is Teflon. And, all right, so what is PFAS again? It has a number of uses. So if you look at the right-hand side, you can see Teflon, PTFE, polytetrafluoroethylene. This is one of the first PFAS molecules ever developed, and everybody has a Teflon coated frying pan or something like that. It's also used in Gore-Tex water resistant breathable clothing like I show here. But the big use, the really, really big use of things, particularly like PFOA and PFOS, is to fight fires, so-called aqueous film forming foam, or AFFF. And you can see here's a firefighter trying to put out a fire. This is a fire for a liquid fuel, for example, jet fuel or something like that. This is widely used at airports and for military bases and places like that to put out fires because it's extremely good at it. And I will explain why it's so good at this a little bit later in my talk. Now, let's take a brief look at the timeline for what's going on with PFAS. And it all starts back in 1939 when the PTFE, or the Teflon, was discovered. It soon became marketed by DuPont as Teflon, and now everybody has it on their frying pans and other cooking devices. Uh, then 3M got into picture, and they started making PFOS and PFOA, and they're the main components of the AFFF, the firefighting foam. And in 1963, the U.S. military began using it, and after a while, they mandated that every military base that had things like jet fuel had to have AFFF around because it was so effective at fighting fires. Now, in my timeline here, you're going to see things with blue boxes. That's sort of development of the products. And then you're going to see things in red boxes. And these are the warning signs of environmental or human health problems. So in 1968, organofluorine compounds were detected in blood serum of people. So it was like 68, we started to see this accumulating in people. In the 70s, they were found in fish. In the 80s, people started looking for them and found them in drinking water all over the country. And then you could see 1998, 3M found more fluorochemicals in blood, human blood. So at this point, we're starting to get an accumulation of evidence that these PFAS molecules are bioaccumulators, and they probably have some serious health problems for people and ecological problems as well. So in about 2000, 3M started to phase out these PFAS molecules from their products on this. In 2009, they were put on the priority pollutant list. And in 2016, the EPA published an advisory for PFOA and PFOS at 70 parts per trillion. That's parts per trillion or nanograms per liter. These are quite low concentrations. These are for things like drinking water. And then very recently in 2022 and 23, the EPA issued some much more stringent regulations on this. I'll talk a little bit about that later, but they're way lower than 70 ppt for PFOA and PFOS. So the regulatory landscape has really tightened up on this. And now, of course, one outcome of that is that things like PFOS and PFOA aren't being used anymore, and other fluorinated substitutes are being developed. Now, this is a family tree of PFAS. It's not to be read in detail, but to give you the idea. First of all, there have been more than 15,000 PFAS molecules developed. They're not all used commercially, of course, but they ranged greatly in size and structure. So if you look at the right-hand side and just look at the big lettering, you've got the perfluorocarboxylic acids at the top. That's things like the PFOA. And then you got the PFSAs, that's the perfluorosulfonic acids like PFOS. But then you can see all these other things down here that have been developed over the many years, many of them designed to be substitutes for things like PFOS and PFOA. And I'm not going to go through all of these, obviously I can't, but there are now a huge number of PFAS molecules out there, and of all different sizes and different chemical structures. So it's pretty complicated. Now, people started looking for PFAS and they looked for them in drinking water wells. And here's an NIH study relatively recently from 2022. And you can just see all of those dots of where they found PFAS molecules in drinking water wells. And you can see where they're located. They're located near military sites. Military sites have airplanes with jet fuel, for example. And military sites have, therefore they're doing firefighting, either actual fires or firefighter training there. You can see airports, same thing. They have jets and jet fuel. You can have wastewater treatment plants. This reflects that the PFAS molecules get into wastewater, and the wastewater itself may be discharged somewhere, or the biosolids from wastewater treatment will contain some of these PFAS molecules. They may be applied to the soils. And you have the industrial facilities, which include industrial facilities that produce PFAS molecules and also those that use them. I'll say a bit more about that in a few minutes. Now, let's talk a little bit about why PFAS molecules are so persistent and therefore such a problem. Uh, they are called the forever compounds because they don't break down at all, or at least not readily under normal environmental conditions. And one of the reasons is because of the CF bond. You can see, as I represented it up here at the top, it's a very polar bond, where the F is contains most of the electron density. It's sort of negatively charged, and the C is deficient in electron density. That bond, because of the electronegativity difference, is a very short bond and is physically short and very strong. And you can see down here the bond association energy to break that bond is by far higher than any of the other ones that we have down here. And so this is really quite a strong bond. So one of the reasons that it doesn't break down under normal environmental conditions is that the CF bond is just super strong. This is exacerbated by for perfluoro compounds because the whole molecule is covered with these CH bonds. So there's really no easy opening, for example, for an enzyme from a microorganism to get in there and start to break it down. So the perfluoro aspect plus the really strong bond makes this extremely difficult set of molecules to begin the breakdown process. At the same time, it's hydrophobic and it's lipophilic. And so that's because they have parts that are polar, like for example, in PFOA, you've got the carboxylic group at the end that's negatively charged, and that's lipophobic. But then you've also got that long chain, the other 7 carbons, the fluorines that are very hydrophobic. So this is great for making frying pans. It's really great. The hydrophobic part is really great for making frying pans. Things don't stick. It's really great here. But as I say in red letters, that hydrophobic nature is also great for bioaccumulating in the food chain. And so what we see is that these PFAS molecules do bioaccumulate very strongly, and they go up the food chain. So not only are we getting exposed to PFAS molecules from, say, drinking water, but we're also getting them from the food we eat because this is a bioaccumulator in the environment. Now, AFFF, firefighting foam. You can see here on the left a picture of some firefighters practicing putting out a fire. So it'd be something like jet fuel on the ground, and it's burning, and they are spraying the AFFF on it. Well, you can on the one hand, you can see why a lot of this AFFF gets out in the environment, because these firefighters, whether they're fighting a real fire or they're doing training, are just dispersing this out in the environment. It's just going to get out into the soil, into the water, into the air. And so one of the reasons why you see a lot of PFAS molecules around airports and military bases is because they do things like this. And this is what the molecules were made for. Now, it really works great, though, and that's shown on the right-hand side here. Why is this AFFF so wonderful at fighting fires? And why did the United States Department of Defense mandate for many decades that all of its facilities use it? And what it does is this. It's first of all, it spreads rapidly across the surface of a fire. Now, there's a fuel like jet fuel down here, and the jet fuel catches on fire. And so they come out there and they spray the foam, and the foam, because the molecule is a surfactant, if it forms a foam, and then it basically slides along, forming a blanket that goes across the fire, and it eventually covers the whole fire and suffocates it. Now, to have a fire, you need a fuel, you need oxygen, and you need heat. Well, if you can suffocate the fire, that is, you can eliminate contact with the atmosphere with oxygen, then of course you can stop the fire. And so the AFFF is tremendously good at spreading like this. Its spreading capability is exceptional. It suffocates the fire. Plus, it's a forever compound. It doesn't easily break down, so the AFFF molecules don't themselves combust. And because they don't combust, they stay there and they continue to put out the fire. So this is a remarkably wonderful material for doing this job of fighting fire. So that's why, again, the military has mandated it, and lots of other people use it for the same purpose. All right, now, and I'm going to come back to that in just a few minutes, talking about, well, if we don't use AFFF for this purpose, what do we use? I'll come back to that in a minute. But before I do that, let's talk about where these PFAS molecules come from. And so here's a little drawing of human society and all the things that are going on and interacting with the environment. And so what are the sources? So the first of all, they're industrial sites. So these would be like industrial sites that are making the PFAS molecules, things like DuPont or Dow that are the manufacturers of PFAS molecules, or 3M is another one. And so they have wastewater discharges. Some of the PFAS molecules get in their wastewaters. They have other wastes, solid waste that may have PFAS in them. And of course, some of the PFAS molecules are volatile. The smaller ones are volatile. They can go out, say, through stack emissions. And so you've got the industrial sites that produce the PFAS molecules, their sources. And then you've got the uses of them. And I just showed you fire training Well, you got to train the firefighters to use the materials they have to use, and so they're going to use it. And as you saw in my picture, it gets spread out all over the environment. Then you've got the actual firefighting, say at an airport, and the same thing's going to happen. And of course, you can have leaking tanks or things like that that occur at these use sites. And then we have landfills. And landfills, of course, uh, take in all the solid waste that we generate, and we generate a lot of solid waste. And so you have industrial waste from either perhaps the manufacturer and certainly the industries that use PFAS molecules that contribute solid waste. And of course, consumer products. It's in our clothes, it's in our frying pans, it used to be in things like McDonald's hamburger wrappers. And so these things get deposited in our solid waste stream and they get out into the landfills. And eventually they could leach out into the groundwater. And then wastewater sludges. These PFAS molecules get into the wastewater. They bioaccumulate in the biosolids or the sludges that get disposed of frequently in landfills. So you can see how landfills become a significant source. And then you've got the wastewater treatment plants themselves. And I'm talking about wastewater treatment plants for domestic sewage, for example, and they have a lot of possible emissions here. I'll highlight the two of them. One is air emissions. The smaller molecules can be volatile, and so when you're doing aeration of the wastewater, you can volatilize some of the smaller molecules. The larger molecules are largely going to absorb onto the biosolids, and they're going to go out with the biosolids to landfill or to land applications, say even for agriculture on this. And so these are all sources here. Now, I do want to point out one interesting source that I'm aware of, and it should be of interest to all of us because we live here in Arizona. Uh, Semiconductor manufacturing. Semiconductor manufacturers use a lot of PFAS molecules, and they have problems with PFAS in their wastewaters and maybe even gaseous discharges. So Arizona has now become a hub for semiconductor manufacturing in the United States. And so I could tell you the semiconductor industry is very interested in ways to minimize or completely eliminate the discharge of PFAS molecules from their manufacturing facilities. All right, so as I showed earlier on the timeline, we began to discover these PFAS molecules accumulating and starting to cause health effects. And so some of them, like the PFOA and the PFOS, got banned around 2000. And you can see here in the left-hand side, this is the average blood PFAS level of these particular molecules, some of the most widely used ones. And you can see they're starting to go down. They're going down, 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 down. So PFOS is very dramatic decrease. So as we ban these materials from use in our society, we do see less of them in humans, for example, in the blood. Of course, these particular molecules are being substituted out and replaced by other PFAS molecules that aren't these four, but something else. And so we might expect that the other ones are going up. I don't have the data for the other ones, but we can imagine that some of the other ones are going up. So why do we care about PFAS in human blood or anywhere in the human body? And here's a list of known health effects. Now, I'm not a medical person. Don't ask me questions about the details here because I don't know the answer, but I do know that the health experts are very concerned about these four negative impacts of PFAS in humans, interfering with the hormones, endocrine system, increased cholesterol levels, affecting the heart, uh, affecting the immune system, and increased risk of certain cancers. So these have already been shown to be true, and this is why PFAS molecules are either being banned or the EPA is putting on some really strict limits on them in things like drinking water. Now, of course, if it's a bioaccumulator, it's bioaccumulating in everything in the ecosystem and not just in humans, and it's in the birds and the fish and everything in between. And so we know that it's bioaccumulating. We've made the measurements to show the bioaccumulation in the fish and birds and things. That's known. What isn't known very well is what are the either health or ecological impacts of this bioaccumulation in the environmental species. And so, you know, there are people who study what he calls ecotoxicology. That's not me, but I do read some of their work. And a recent study trying to summarize what we know said, well, we have a paucity of data on the effects in the birds, fish, wildlife, invertebrates in general. So we don't really know. We know it's accumulating, but we don't know very well what the effects are. Uh, People are trying to assess the effects, acute and chronic, on this, but it's hard. It's hard to do. It takes a long time and it's expensive work. So the information on this will be coming out gradually, but it's still kind of limited on this. All right, so we know we got problems. We know it's bioaccumulating. We know it has health problems on humans and probably in the environment too. So what are we going to do about it? Well, one thing we can do is we can stop using the most troublesome molecules. And so the AFFF is an example. It was, again, widely used for fighting fires, very effective for doing that, but it has a lot of problems. And so the United States Department of Defense, along with the companies that manufacture things like firefighting foams, are trying to find substitutes. And I know the Department of Defense has spent, I don't know how many, countless millions of dollars trying to find substitutes on this, and it's going slowly. And I'm just going to show you one example. This is from a paper that I saw recently where they were using a non-fluorinated um, firefighting foam. And you can see on the right-hand side here, here's the fire's going great. I mean, it's really going great, but you begin to get some control at 90 seconds after the foam. You can see the foam on it. And then you get about 99% control, 36 seconds, 43 seconds. It looks like the fire's out. Success, right? No. Turns out that foam, firefighting foam, not being a perfluoro compound, eventually either is combusted or volatilizes and the fire comes back. So this is the big problem that they're having right now in finding replacements. It's hard to find something that will have the combination of spreading and putting out the fire, like you see here, but not itself being either volatilized or combusted. And so this has been very slow work, very, very slow work. They're making progress on it, but it's far from a solved problem. All right, so now I'm going to talk about things I know a lot about, and that is the treatment of PFAS molecules. It would be in our water or in our wastewater. And this is my business on it, and so I'm going to give you a general overview of what's being done now, and then I'll towards the end of my talk, I'll give you a little overview of what we are doing, which we think is a very effective means of controlling and actually destroying the PFAS molecules in water. So here we go. Today, if you have PFAS in say your drinking water and you've got to remove it, you basically go with we call a separation technology. And the two options here, I've illustrated those. The first one is adsorption. That is, you get the molecules to adsorb on the surface of something that's very good at absorbing it. And so the two adsorbents that are widely used are activated carbon and ion exchange resins. So if you look down here on the lower left, you've got activated carbon, a little cartoon of how this works. And so the molecules are adsorbed onto the activated carbon due to the molecules, the PFAS molecules having a large hydrophobic component. So if you have a long chain, long carbon chain, it's quite hydrophobic. It will absorb very strongly in the micropores of the activated carbon. And the longer the chain, the stronger the absorption. Very short chains don't absorb as much. In ion exchange resins, the principle is the same in the sense that you're going to absorb, but now you're going to actually focus in on the charged part. Like in the PFOA, it's the carboxylic acid, negative charge, or PFOS, it's the sulfonate group that's negatively charged. And you're going to get, then the absorption is going to be based largely on the charge on this. So both of these are very good at removing ones that have either a long chain for activated carbon or a high charge to mass ratio here in the ion exchange resins. Now, the other alternative is a membrane technology like nanofiltration or reverse osmosis. And here you're pushing the water through a membrane that has very tiny pores. And those pores are small enough that the large molecules can't get through. And so you retain the large molecules, and in this case, the larger PFAS molecules, like the C8 ones, PFOA, PFOS, they would be very well retained. However, the smallest molecules, the ones that have 4 carbons, not 8 carbons, might slip through. So this is very good at removing the large ones, but some of the smaller ones will slip through. So these separation technologies can be very effective at removing these PFAS molecules from the water, but they don't destroy the PFAS. They're just moving it from one place to another place. And as I pointed out, they don't work as well on the small molecules. And there's been efforts within the industry to use more small molecules instead of long molecules because the small molecules are less bioaccumulative. Okay, but it kind of works against these removal technologies. Okay, now that was for just removal, and that's what you would do today if you had a drinking water supply and you had to remove it. That's a tech commercially available. You can do it right now. Now, if you want to destroy it today, the most commonly used methods to destroy the PFAS molecules are what we call AOPs, advanced oxidation processes. And in an advanced oxidation process, you generate free radicals, and I'm showing here the hydroxyl free radical as an example of it. And that hydroxyl free radical is a very strong oxidant and attacks the carbon-carbon bonds, breaks the molecule into smaller pieces. It doesn't defluorinate, but it does break it into smaller pieces. And now in my diagram, I've shown 3 common examples of how to generate free radicals. One's called the Fenton reaction, and it involves using the iron, which is very labile, to change between iron 2 plus and iron 3 plus, and then in the process, you can generate these free radicals. Another one is to use UV light and hydrogen peroxide. Same thing. The energy comes from the UV light, converts hydrogen peroxide into free radicals. And then over on the right, you can use UV light and photocatalysts like titanium dioxide. Same thing. You generate free radicals at the surface of these. So these advanced oxidation processes are pretty mature technologies in general. They're being applied for PFAS molecules. They're kind of expensive. You have to put a lot of energy in to do it. They don't really destroy the PFAS molecule. They break it into smaller pieces on it. And as I just said in the prior slide, those smaller pieces may be harder to remove than the larger pieces. And so advanced oxidation doesn't completely solve the problem, and maybe it makes the problem worse in some cases. So that's something to think about. Okay, now I'm going to be making a transition here to talk briefly about what we are doing in my team for destroying PFAS. And the core of our work is the mechanistic understanding of how we're going to break the carbon-fluorine bond. Advanced oxidation, I just showed you that, doesn't do it. It breaks carbon-carbon bonds. We need to break the carbon-fluorine bond, so we don't have fluorinated organics anymore. Now, what we're going to do is we're going to take advantage of a very important chemical characteristic of the element fluorine, and that is it's extremely electronegative. Here's the Pauling scale, and the bigger the number, the more electronegative it is. And you can see by far fluorine has got the biggest electronegativity. I'm comparing it even to chlorine here, which is also famous for being electronegative, but fluorine is much more electronegative. Electronegative means that this element, chemistry-wise, has a great affinity for attracting electrons to it. And so if you've got a bond, say between carbon and fluorine, the fluorine, because it's so electronegative, controls most of the electron density around it. And it also means that this fluorine element is susceptible to taking all of the electrons, and breaking the bond and just becoming fluoride ion. That's called defluorination. It would be reductive defluorination. And this, we predicted, would be an excellent way to begin the process of removing those fluorines. So that's what we're trying to do. So we have a system here we call the synergistic platform that does this. So we use hydrogen gas as a reductant to defluorinate. Let's remove some of the fluorines, and then we deliver those defluorinated products to a biological reaction, to aerobic, in which the microorganisms finish the job of defluorination and also mineralize or completely oxidize the carbon. Thus, the molecule is totally destroyed here. So we can run these two things in series as I show here, and a little more detail here. Here's how we actually do it in the laboratory. So we have two reactors in series. The first one is something called the hydrogen-based membrane catalyst film reactor, in which we have gas transfer membranes that deliver hydrogen gas, the reductant, and we deliver it to a film of precious metal-based catalysts, which are really good at doing reductive defluorination. And then you get totally to partly defluorinated compounds, and that's delivered over to a biological process. We call it the membrane biofilm reactor, which we have bacteria who then will complete the defluorination and fully oxidize the products here. So that's just how the system works. So the first stage is using palladium as the catalyst. Palladium is a wonderful catalyst for doing reductive defluorination. And the way we set it up, we have a system where we have these hollow fiber membranes that are being delivered hydrogen in the inside. And the hydrogen goes to the outside, and it forms palladium nanoparticles on the exterior of the membrane. That's what we call it, the catalyst film. And I'll show you a picture of that, how that works in just a minute. But here at the end, you get this. You get these black coated membranes here. By the way, the membranes are white before we do this, and when you put the deposit the catalyst film, they become black. All right, so we use platinum group metals, particularly palladium, because they are so good at catalyzing reactions like this. They're widely used in industry for all kinds of reduction catalytic reactions. You can see where they lie on the periodic table, where we focus most on palladium because it's really good for reductive defluorination. These are precious metals. They're very expensive. There aren't very many places in the world where you can mine them, which is a great supply and demand thing, making them quite expensive. Okay, so here's what we do when we deposit it. Here are the membranes. You can see the membranes here are light colored. We add a solution of palladium 2+, that's soluble palladium, oxidized palladium. We start delivering hydrogen through the membrane, and after a while, we get all the palladium. By the way, palladium 2+ in water is reddish like this. And eventually you see the red all goes away, and you get all the black on the membrane. So we've now deposited all the palladium as elemental palladium nanoparticles here. Now we've got the palladium nanoparticles on the membrane, and we can use it. And so we can use it to do defluorination. I've shown one simple example here. This is a batch reaction where we just added PFOA here at 100 micromolar. In this left-hand panel, we didn't have any palladium, no palladium, and nothing happens. PFOA doesn't go down, And this would be the other one down here, the little blue triangles would be released fluoride, nothing happens. But if we have palladium, like I show up here, then you can see the PFOA goes down and the fluoride goes up. So we're getting the we call reductive defluorination. We are removing the fluoride from the molecule. We can do this on a continuous basis. And this is an example of one of our continuous reactions. You can see we're feeding in at about 8 micromolar. That's going in, and we're coming out over 90 days at about 10 or 15. And you can see the fluoride here. The gray is the released fluoride. So we can do this continuously. The process continues to work very well. Okay, so now we're doing this in the first stage. We're removing some of the fluoride, and now we're going to deliver it over to the second stage here, where we're going to let the microorganisms take over and finish the job. So we'll take a look here at the something with the stage 2, the biological stage. So we grew a biofilm, aerobic biofilm, on octanoic acid, completely non-fluorinated compound. It's totally removed. We then initially added an easy one, 2FOA. It's 2-fluorooctanoic acid. It has only one fluorine on it. Here we added it here and here and here. You can see the concentrations added in the black boxes. And you can see after some time, it's completely gone. And the fluoride ion is stoichiometrically released. So for an easy one, only one fluoride, it worked great. And then we went to a hard one, 13 fluorines on this molecule, 2-HPFOA. And it took a little longer to do things, but you can see down here that we were getting substantial defluorination and substantial removal of even only 2 fluorines removed. So the second stage works, but you can also see that if you remove more fluorines, you get faster and more complete biodegradation of it in the second stage. Okay, so now let's put the 2 stages together and actually run it sequentially like I show here. And what we have here then is a situation here where we were in the red boxes. We did it exactly like I showed you in the previous one. And you can see here, this is the PFOA has gone down about 85% here totally. This is effluent from the first stage, effluent from the second stage is about 85% removal on it. And if you look over here, you can see fluoride release is from both stages. You get the larger amount from the first stage, but you get additional fluoride release from the second stage. In the blue boxes, we just put a recycle on it, give the molecules a second chance to go through the system, and you can see when we do that, the PFOA goes down even further, essentially almost 100% removal when we did a recycle on it. So we got really quite good results with the 2 systems running in tandem, just like I showed you in the diagram. So I'm at the end. Take home lessons from my talk. Number 1, PFAS are everywhere. They're in water, they're in soil, they're in sludge, they're everywhere because we use them in so many ways in our modern society. They're bioaccumulators. We've seen the bioaccumulation in the environment. We see the bioaccumulation in humans. In humans, we have documented negative health impacts, and I've listed them, effects on the immune system, cardiovascular system, development, and cancer. So these are serious, serious contaminants and very big-time bioaccumulators. Now, the treatment targets are moving to very low levels. Very early on, I mentioned that the EPA established a target of 70 parts per trillion for PFOA and PFOS. In the last year, 2 years, they've lowered that to 4 parts per trillion, which is really hard to measure. It's so low. Okay, so you can see the seriousness of these impacts of PFOA is leading to some very stringent requirements from the EPA. Now, today, if you're going to remove it, you're either going to use either adsorption or you're going to use separation device, a membrane separation device. These work, they remove most of the molecules, particularly the larger ones, but they don't destroy it. They just move it from one place to another. And now you've got to deal with your concentrated adsorbent or your concentrated brine in the reverse osmosis. And what we're doing, the last thing I described, is reductive defluorination using a membrane catalyst film reactor to remove some of the fluorines to make the PFAS biodegradable. And then the microorganisms in the second stage can complete the process, complete defluorination, and completely oxidize the carbon here. This is a system that we consider to be completely compatible with existing water, wastewater, and water treatment systems. And so we think this can be easily integrated into existing systems to actually destroy the materials, not just move them around to another place. And with that, come to the end. Thanks for listening. And if you have any questions, I'm here to answer them. I'm not sure exactly how I'm supposed to do this, but someone will tell me. So thanks, Al. Okay.
Thank
How
you.
do I deal with questions?
Yeah, I'll go ahead and read them off to you.
Okay, good.
Yeah. So here we go. The first one. What is the potential for widespread adoption of defluorination, and what is the likelihood that 3M, DuPont, TSMC, etc., will bear the cost of these projects?
Well, I mean, I'm a little biased, of course, since this is my baby, but I think there's quite a good chance. I mean, first of all, we work already with TSMC, so they're already onto the problem, and they're all already partnering with us, and they really want us to take our technology out to one of their facilities here in Arizona to try it out. That's pretty strong evidence. We also are in contact with some of the leading environmental technology companies who are very interested in also partnering with us to help actually make the technology be commercially uh, available. So there's quite a lot of interest. Now, I will just say we don't have any idea what's going to happen with what I'll call the regulatory push. Things have changed. I'm not going to have to explain to this group what that means, but I mean, there is some possibility that things will get slowed down just because the regulatory emphasis might be diminished a bit. I hope not, but we'll see.
Thank you for that answer. The next question is, how practical is what you're doing in the lab to large scale and real world application, cost, time,
Yeah,
etc.?
yeah, right. Well, that's of course the question that I always get asked, and it's a good question. Uh, so we've demonstrated this quite thoroughly now at the bench scale, and what we're doing now is we're designing a pilot scale system that we can take out to the field. So we could go out to a TSMC site, or we could go to a wastewater treatment plant, and and uh, and show that this works in the field with real waters under real conditions. That's what we're trying to do right now. We have a spin-out company from ASU that is working exactly for this kind of commercialization. So we're doing all the right things. It takes time. It's not going to happen overnight, but we are doing all the things we need to do to get there. Oh, but and a big issue is cost. And there's no doubt about it. And we've done some preliminary costing on this. And I mean, the biggest cost factor currently is the cost of palladium. Palladium is expensive, and we really need it for for the membrane catalyst film reactor. So what we're doing and working very hard in our research is finding ways to substantially reduce the amount of palladium we need, and therefore substantially reduce the capital cost.
Thank you. And I'm taking notes as you're speaking, so sorry it's taking me a moment.
Okay.
All right. Do the PFAS naturally break down in the environment over a long time frame at all?
Could you read? Oh, does it break down? Oh, yeah. Well, okay. So I can answer that in two ways. Way number one, there are like thousands of different PFAS molecules, and they're all different. Some of them are going to break down more readily than others. And if you have something like PFOA or PFOS, that's going to be the slowest. It's completely perfluorinated. It's just, we know it's really, really slow. Some of the other ones that, that are not perfluorinated, but have essentially places on the molecule that don't have fluorine elements everywhere, they may well be more degradable either through biodegradation or photo hydrolysis or something like that. So there's no one answer on it. Of course, the ones we're most concerned about are the ones that are the really recalcitrant ones, the ones that truly are forever compounds. And there are a number of them that were in very common use that are out there that are the breakdown under environmental conditions really is going to be slow.
Thank you. All right, looks like our next most popular question. If blood content of PFAS have been coming down dramatically since 2000, why is this such a big and well-known issue now?
Well, they have been coming down because we banned the use of certain chemicals, and so it's good to know that that we're not putting them out in the environment. They're not bioaccumulating more, and it's going down. But the key thing, there are two key things here. One is there have been substitutes, and we don't know as much about the fate of the substitutes on it. Theoretically, the substitutes are less harmful, but that's theoretical. We really don't know on it. And the second thing is, even though the concentrations have gone down, that doesn't mean that they're down to levels that have no effect. And I'm not the person to tell you what's the no effect level for PFAS in your blood. I have no idea. But the fact that the EPA is promulgated these extraordinarily low concentrations for drinking water, 4 parts per trillion, means that they think that this is really a serious problem, even though levels have declined over the last decade or so.
All right. To accommodate this process, what size plant would such a process need to be?
Well, so that's a good question. And so I can't give you, I can't give you an answer. 2 reasons I can't give you an answer. Number one reason is every situation is different. So what are the water flows? What are the concentrations? So everyone's going to be different. So there's no, one size fits all answer on this. When our job, one of our goals is to make a very compact process because, for example, you go into a semiconductor manufacturing facility and maybe it's already built and they're not going to want to build an entire new complex just for treating the water. So we want to make things that are very compact that'll fit in or right next to the site, and they'll reduce the capital costs and make things much more feasible. So one of our goals is to make things that are quite compact. The system is modular, and so each module will have a certain capacity for removing the PFAS molecules, and then we look at the mass flow of the PFAS molecules that are removed, and we say, well, we need 4 modules or 10 modules or 20 modules or something like that. And that's how we go ahead and design the system.
Thank you. All right. Our next question. Knowing this is in the water system, will this be a known contaminant that the water treatment plants will test for?
Yes, they're now required to test for this, and that's how we know. When I showed that map, where all the contaminants were, that's how we know because people are now required to test for it. A couple of members of my team here are right now making a very sophisticated analysis of the occurrence of these PFAS molecules in Arizona. Arizona has quite a substantial database on this, and we're utilizing that database now to really get a very sophisticated analysis of one, where's the problem and what's it associated with? Is it associated with military bases? Is it associated with manufacturing plants or something else? And so this is one of our goals is to help allow us to focus our energy on the most critical places.
Right. Next one. Are any small drinking water systems in Arizona currently treating for PFAS removal, PFAS removal?
Um, I, I really don't know that answer. I I wouldn't be surprised that the answer is yes, but this is just, this is a level of information I just don't have.
Do other metals work besides palladium, or
Yeah.
I don't know.
Yeah. That's a good question. And the answer is yes. I mean, we have tried a whole range of all of the most of the platinum group metals. They all work. Palladium works the best, and I can just explain briefly why palladium is so good at this, and we want to have, palladium involved. So to make the catalyst work to do this, you need two things to happen. You need the PFAS molecule needs to absorb on the surface of the palladium, and nearby we need to absorb what we call activated hydrogen. And so palladium is very good at absorbing and creating activated hydrogen, and it's also very good at absorbing the PFAS molecules. And so it gets all the two components that have to react together, it gets them close together very effectively on this. And so we always make palladium part of the catalyst story. But palladium isn't perfect, and so we are working very seriously on combining palladium with other metals that overcome some of the deficiencies of palladium. Well, I mean, one deficiency, of course, is palladium is expensive, and so we try maybe make we call an alloy, say a two metal alloy here that has a similar reactive properties, but doesn't cost as much. So that's something that we're very interested in doing.
Thank you. All right, the next one. Are any home filtration systems effective at removing PFAS?
The answer is probably yes. I haven't seen anybody who's actually exactly studied this topic and published it, but one would expect that your home systems properly maintained will work. I mean, in most home systems, you have ion exchange, you have activated carbon, and you have reverse osmosis. They're mainly there to remove salts, and they're good at it, but so all but the smallest PFAS molecules ought to be removed by those in-home methods. But the key thing, of course, is that you have to maintain your in-home method. There's an absorptive capacity for the activated carbon, for example. You can overwhelm it and then it won't absorb anything. And likewise, you have to maintain that reverse osmosis system. So it requires good maintenance, good operation of it, but it ought to work for most of the molecules.
Good to know. All right, our next one. Where were the scientific studies before the approval to release PFAS into the environment?
I didn't quite catch that. Could you try that again?
Yes. Where were the scientific studies before the approval to release PFAS into the environment?
There weren't any. I mean, so that's not the way the system worked, and so, 3M and DuPont, they developed these molecules. They had, very valuable functions, everything from fighting fires to, Teflon on your frying pan. And there's nothing requiring them to really test for bioaccumulation or human health effects or ecotoxicity. So they just did it. It was years later when we started measuring and saying, whoa, we've got these PFAS molecules in our blood serum. Well, okay, now people start to look back and say, well, where did it come from? And so, yeah, ideally, we would be forward looking, but the reality is we're almost always backward looking.
Hopefully that changes. We'll see.
Yeah, well, I mean, we have moved in the right direction. I don't think we've perfected it though.
Yeah. All right, our next question. What are the other waste products from the first membrane defluorination process?
Yeah, well, there really aren't any waste products. So the water goes into the first stage, you do reductive defluorination, and you produce a suite of defluorinated products. And we've measured this, very carefully. And so if you have like PFOA, that's got 8 carbons, 15 uh, fluorines on it. When you look at what comes out, you got some of the PFOA molecules are completely defluorinated, no fluorines left. And others maybe have, you know, two or three fluorines left. Others may have 6 or 7. Some of them may have, 13. So you're going to get this mix here of things. So that water then moves to the second stage, the biological stage. And as I briefly showed, the ones that are really defluorinated, there's like no fluorines or only a few fluorines, they're going to be completely destroyed. And we don't know for sure what's happening to the other ones. That's part of our research to try to, understand that. So we make sure we design the systems and operate the system so it, gets complete defluorination. But there's no real waste. I mean, it goes from stage 1 to stage 2, and there's really no waste from stage 2. There's the effluent, and whatever's in the effluent goes out, but to wherever it needs to go. But there's no really other output stream of these processes.
Interesting. Thank you. All right. Our next question. Do you recommend an integrative approach to environmental health as a way to cellular detox the PFAS?
I'm sure I do. I'm not sure what it is though. Um, it's I mean, so on the one hand, what I deal with would be the exposure. You got the humans are exposed through the water, maybe through the air and other things, and certainly the food they eat. So things we do would be addressing the issue of minimizing exposure. Now, once it's in the human, maybe there is a way to detoxify the human to get it out. I have no idea how that would work. That's not my business. So, but I would think that given that we have a lot of PFAS in people and animals, that we might want to think about how to get it out. Beyond minimizing the input, which is what I do.
Minimize the input.
Yeah.
Thank you. All right. Our next question. With the current nanofiltration, etc., what are the disposal processes for disposing the contaminated filters?
Oh, that is a wonderful question. So yeah, so you do say reverse osmosis or nanofiltration, and then you got this concentrate that's left behind, and it's got the PFAS molecules and other stuff in with it. So then what do you do with it? This is not a resolved issue, I can tell you. And I'm involved with large research programs where people are addressing this, and I can tell you that it's not been solved, particularly in water. Um, I mean, if you have it, if it's not in water, let's say you have granular activated carbon, you remove the granular activated carbon, you remove the water, you can incinerate it. I mean, if you really incinerate it at a high concentration, everything is destroyed. So that's a possibility. But if something that's in the water, like the concentrate behind from reverse osmosis is not, you're not going to incinerate water. So actually, this is one of our focus areas now is dealing with these concentrates, particularly from reverse osmosis, and how we can use our system now to destroy the PFAS molecules because it's still in water, just at a higher concentration.
Thank you. And just so you're aware, you have so many questions. Is
Oh
there any
boy.
chance that after this, you could type in the Zoom chat your email, if you don't mind sharing?
Oh, okay. Yeah. Okay. Sure. Let me see if I can figure out how to do that here.
Yeah,
Chat.
no worries.
Yeah. All right. Okay. Here we go.
I think we have time for another one or two, but I'll
Okay.
have you
Here
do
we go.
that just right now, if you don't mind.
Let's see. I just typed in. Let's see. Make sure I typed it right. Okay. I did. This should go out to. I think it goes out to everybody here. Well, we're going to see.
Looks good.
Okay. We did it. Success.
Thank you. All
Okay.
right, our next question. Outside of the Phoenix and Tucson metro areas, are there other parts of the state with a known PFAS in groundwater problem?
Oh, yes. Yes. I mean, it's everywhere in the state. Every place that we're sampling, we find PFAS. And, like I said, I have a group in my team looking exactly at that. And we have a map, and it's everywhere where it's being sampled. Now, there are some open areas like on Navajo Nation where there's almost no sampling, and we don't know. So that's a not know, it's not a no, it's a that we don't know. But every other place where people sample, it's just the map is all over Arizona.
Okay, thank you. All right, I think this is the last question.
Okay.
Well, actually, we're out of time. Well, thank you so
Okay.
much. I will email you with the rest of the questions.
Okay.
Um, but yes, everyone feel free to email Bruce
Oh
if you
boy.
have any other questions about his
Okay.
research.
Okay. Very
Thank you.
good. Okay, you're welcome. Glad to have a chance to meet with everybody. Bye now.
Awesome. Thank you so much for your presentation, Bruce.